Today I have a pretty interesting topic to talk. It's about identification process in recirculation zones. And my main idea here will be to pass to you a little bit of my experience in such a cases. I will also show interesting case we had on a project, on a client project. And I will talk about the identification, the simulation assessment, validation, and at last, a summary. So just to start, recirculation zones are actually zones with the presence of separation flow, the wind with flow separation, or presence of reverse flow. Usually happen when the site is so steep enough, causing the wind not to follow the terrain, and then causing these vortex-like patterns. Right, and those areas are characterized by significant lower in wind speeds, direction changes, and sometimes even extreme values of turbulence and shear. It's so important to analyze these cases because placing a turbine on these situations is usually not the best idea, but sometimes necessary. Sometimes due to the restrictions or due to ambient due to the distance between turbines, it's actually necessary to put it a little bit not on the top of the hill, but on a lee side of the mountain. And this will increase the loads on the turbine, but most of the times can be managed by applying sector management. But failing to proper analyze this phenomenon can transform to be chaotic for the project, and sometimes even killing the project due to the amount of curtailment necessary to prevent failure in the turbine. So I'd like to start showing this case that came to us. It was first analyzed by a consultant, and in this case was using a linear model. And this is not at all a criticism to the consultant, because if I had to bet, I would say that the client paid for it. So CFD analysis is usually more expensive than linear models. So I don't think it was a judge came from the consultant, but rather the client. And to explain a little bit about this site, we have obviously a complex terrain. The measurement mast is in a little bit higher position than the turbine positions. And the turbine positions were being covered by the mountain that was, this is actually the north side of the site. The image here, it's a little bit messed up, but it get the idea. So you can see that the whole rotor area was covered by the terrain. And when it came to us, it came with the idea just to perform the load assessment. But then we analyzed it and see that then the site was analyzed using a linear model. So we did the analysis again using a proper CFD calculation. And we noticed that there was a bit of uncertainty on the predictions of the met mast. And the only way to prevent and to make sure that turbines would be fine at the site was to apply a curtailment that led to a 5% estimation losses. Right? That due to the risks of the circulation that you can see quite clear the effects throughout the wind park. And the possible outcomes that if we didn't do that would be that we might have loads issues during operation of the wind farm, possibly causing failure or even kind of other problems. If that was the case, we would have to apply curtailment after operation, so the losses there would be unpredicted. And of course, if the loads issue were high enough, it might have losses due to unavailability of the wax. So to start a little bit talking about the identification process, the hints are usually there as soon as you got the information. For in my case, we received the data with already measurements performed, and most of the cases, the turbine positions were already defined, right? But looking at the data, you can already see a few hints, right? For example, I have two interesting cases to show you guys here. And first of all, first of which will be these two met mass measuring, and you can notice that although similar, the windrows of these two met masses are a little bit different, and the areas where you have really low frequency coincides really well with the terrain surrounding the met masts. This by itself is not a confirmation of recirculation. You're going to see that recirculation usually cannot be identified but only using one parameter. But it already gives you a little bit of hint that the terrain is indeed affecting your measurement. Another case that you can look for recirculation, the possibility of recirculation, is looking at the turbulence on the met mass. I'm not sure if it's clear, but for example, if you see here in the black line, this is the average turbulence on the site, and it's slightly over the ISC class A, but the site, it's actually not very complex in terms of roughness. But if you look at the orography, and this would be the north sector, the northwest and northeast sector, the met mass is completely covered by the terrain. And with that, we can actually see in the turbulence how high the turbulence gets during this operation on these sectors. So usually a good idea is to check on your points of interest. But in my case, it would be the turbines already there, but in early stage, you might not know where the turbines are. So you might actually check the positions or possible turbine positions, or maybe possible met mass positions, and look for terrains throughout the whole surroundings of these positions. Look where the terrain can actually cover the turbine or met mast. And just to keep in mind that the risk of recirculation will increase by the distance of this obstacle and by how much it's covering. For example, a mountain at 1 kilometer covering the lower tip of the turbine will be less critical than a mountain at 500 meters covering the whole turbine. Okay, so this would be first talk about the input check. So after the input check, you go to your model, you calibrate your model, and when you're ready, you start the predictions. During the predictions, I would recommend to look throughout the whole directions, and if you did the pre-check correctly, you already have in your mind what would be the directions that might be problematic, and you can confirm with the predictions. For example, in this case here, I'm showing that, for example, the average speed we can notice at 280 and 290 degrees, we have a significant decrease in wind speeds. Also, you have extreme values of shear and veer comparing with the other sectors. And it's also nice to look the parameters within the whole rotor area. For example, in this case, you can see that turbulence, representative turbulence, has a significant increase from hub height to lower tip. So that would be a pretty good indication of recirculation. Another way to look, it's usually what I'm talking here, I'm putting like a flow chart, and that's usually what I recommend to do, because it builds the case on your head, and you can start this investigation, and it will give you confirmation step by step. So another way I would recommend, and that I would recommend to do it at last, is to check your predictions and check the graphics of your prediction in a visual way. For example, here I'm showing the flow slice, and the flow slice can be seen as a cross section of the wind vertically, right? And for example, you can see clear the noticeable decrease in wind speeds behind the mountain. Another way to do that would be, it's a very similar plot. It would be the slice at constant height. And instead of looking as a cross section, you are looking up on your area. And it's already give you the idea of the position of the recirculation, but also the strength. You can see here we have turbines placed on this direction under recirculation zones, but this one seems to be way more stronger. And at last, it's good to check the path that the winds will go until it reaches the turbines, and any kind of spaghetti-like streamlines will, of course, be an indication that something quite extreme is happening there. Okay, so you did a pre-check, you did the model calibration, you predicted your position, and you noticed that a few of them have recirculation. So what now? What should we do? In that case, we had to validate our model, and the validation part is really similar to the calibration, with a little bit of tweaks. Just to explain a little bit about this graphic, you have the speedups on the y-axis and the directions on the lower axis. This gray line would represent the frequency on your windrows. And in blue, you have the speedups measured from the upmost anemometer to the lowest height anemometer. And in red, you have how well your modeling is seeing this site. So a case like this, I would not be worried at all. There I can see that the modeling is predicting quite well. However, in very complex sites, and usually in sites that you don't have enough input, so it might be that the resolution of your maps were not ideal, you might have something similar to this, right? And for the calibration process, the frequency will have a very big role, right? So you have, in this site here, you can see clearly two main predominant sectors. And on those sectors, the modeling is seeing quite well. And overall, the calibration might look good. So the predicted shear might look really similar from the average, especially if the shear is energy weighted or frequency weighted. But you also can see on this map, it's pretty big errors. And again, for the calibration might not have an issue, but if you look at and you notice recirculation on this area, I would be extra careful, right? And you might think, okay, but there's no much frequency. That might not lead to a big problem. But if you pay attention, when I said about the parameters, the wind parameters, and the wind parameters that the recirculation will have an impact, they are related to both fatigue and ultimate loads. And ultimate loads would not care by frequency. Ultimate loads will care by a single extreme event, right? And a model that is misleading that much might bring an extra problem during the ultimate loads analysis in the mechanical loads analysis. So in that case, I would not trust at all on this sector, and I would try to refine my project. I would, for example, try to look for maybe for high resolution maps, and or maybe try to change the turbulence model. Yeah, just to or if nothing that helps, I have already to think about it. That my model might be overestimating the recirculation issue. But these types of analysis, it's only valid if you have a representative measurement. For example, if you have a case in where you have the met mast on a hill and the predicted turbines on a completely different hill, then nothing can be drawn by this analysis. I don't know how the modeling would be seeing the position, so that I would focus on having maybe another measurement there. Just make sure, I would have a final and reliable result about the recirculation, right? The same kind of analysis can be done I'm talking about vertical cross-check, but the same kind of analysis can be done horizontally if you have two mat masts. Okay, and talking about when we don't have a good representative about the mast, I have two extreme cases, and the first one would be you have your measurement mast measuring on a position that is recirculation free, but your turbine, it is on a possible recirculation zone. So probably your values of turbulence and extreme events will be underestimated. So in this case, it's really advised to close these sectors to mitigate these exceedances just because of the risk, because the condition itself on the turbine might be very underestimated. Another way in case you have, you can also revise these curtailments later in case you place a measurement on these positions. And the other way around, you might have the mat mast measuring under a recirculation zone, but your turbine will be in a recirculation free zone. So most likely your prediction in this case will be wrong, and you might see very high wind speeds predicted at the turbine, which would not be realistic. So just to start a summary here, sometimes very classical cases of recirculation might be quite easy to understand, to check. For example, in both of the cases, you have turbines placed behind the mountain. You have clearly separation of the flow. You have the clear decrease in wind speeds. So that would be quite easy to check. At the same time, potentially not problematic cases will also be quite clear. Right? So when you have the flow attached, you might have recirculation in front of it, but when it reaches the turbine, the flow is already not separating. So probably because the terrain is not steep enough, or maybe the turbine is placed on the hilltop, so no problems is expected. The problem lies when we have situations like that. For example, in this case, it will depend case by case. It's not actually a very straightforward analysis. You have to check if you follow the same script that I told you, you're going to have a pretty good idea and check about more than one parameter. Again, a single exceeding parameter will not be a confirmation of the recirculation zone. But for example, in a case, the first case here, we have a recirculation zone that seems to be occurring due to another mountain that's a little bit far away. So in that case, it might be that the model is bringing a little bit of uncertainty, or we don't have information enough to make sure by how much the recirculation reaches, so how much it extends after the mounting. So this case, it might be complicated to check if any kind of mitigation is necessary or not. And in the bottom, what you can see, a very clear case of recirculation, but a little bit in front of the turbine. But when it reaches the turbine, you can only see the decrease on wind speeds, but not actually the flow separation. And my advice here would be, in case you are in doubt, just mitigate it, or try to validate by a new measurement campaign. So to summarize then, recirculation zones are common in complex terrain, and of course it can lead to turbine loads issues, and I would be more worried in this case for ultimate loads. Right? Recirculation check can start as soon as you have an area defined. There's a few steps you can do. You can check the surroundings, check if there is any part of the terrain that is covering your point of interest. And of course, if you can, avoid placing turbines in areas on the lee side of the the lee side of the mountain, try to place them on the mountain top. Remember that a single exceeding parameter is not enough to identify the recirculation. Usually the recirculation shows more than one parameter exceeding. So again, look for, throughout your rotor area, look for differences in turbulence, look for extreme values of shear, extreme values of veer. And of course, the model of course have an effect here and might be overestimated or underestimating the recirculation zone. So it's really important to have a representative measurement. Also, sometimes depending on how complex the terrain is, it's a good idea to use high resolution maps. Please do not use linear model in such a because they were not suitable to investigate recirculation areas. And at the end, the final decision will be like a risk assessment decision for load mitigation. It might be that you have a really good representative measurement, and you see recirculation there, but on the prediction you see you are confident in the prediction. So due to risk, you don't actually need to mitigate anything. You just need to mitigate enough that the turbine passes loads, right? But the other way around, if you are in doubt, check about what will be your reward or that you might get. For example, if you notice that the frequency it's just too low and the IP loss will be I don't know, less than 1.2%, it's better just to mitigate, just to make sure your turbine will be safe. So that was all. Thank you very much.
¿Hay preguntas? ¿Tenéis preguntas?
I've seen in some mesoscale maps in Brazil actually that downhill in the main wind direction we get like higher wind speeds that could be misleading according to what you presented us. Should we always expect lower wind speeds right after the hill?
No, it will depend on how steep. It depends on other factors as well. For example, there's a really good case study in a Perdigão site in Portugal. It's a really good paper. You can read about it. It will explain a little bit about the physics behind the recirculation. Right? For example, it will not depend only, it's not always like that. Behind the hill, we will have a recirculation. It will depend on stability, the wind speeds that you have there. But yeah, it has to be checked case by case.
Okay. So we could expect higher wind speeds sometimes depending on the site conditions.
Maybe, yes.
Okay.
Sí, si puedo agregar algo, claro que muchas veces la aceleración está en las zonas de la montaña, lo más alto.
Pero justo después...
Sí, bueno, luego si quieres lo conversamos, pero sí. No sé. Y hay los modelos lineales, que es lo que le explicaba, muchas veces no lo pillan y no... Necesitas tener temas mesoescalares donde entran temas térmicos, horarios y más.
Have too much of a voice.
That's fine.
But is there a way to take advantage of these recirculation zones that you could identify?
I don't see how. Actually, this recirculation will actually increase loads there, right? And there is big uncertainty related to them, right? So I don't see. I think in the most case scenario, the best case scenario, you won't need to apply any mitigation. Okay.
Do you have any experience measuring upflow? Would you suggest it for these kind of cases?
Yeah, about the measurement, usually is not. We receive the project with the measurement done, but usually we don't see any problems there. The problem is after the wind passes through the mountain, right, and when the lee side is just too steep, and it causes this deceleration and also the separation of the flow.
But do you think that it could be a good thing to have, like a signal of upflow, vertical wind speed? instrument?
Okay, got it. Usually we don't use that information on our assessments.
Toma.
Yeah. Do you know if there's any like recovery distance between a steep slope, or it's up to case?
Yeah, it depends case to case. But for example, one thing you can use as a risk assessment would be the distance between, for example, if it starts to get more and more critical, and you can divide it by 4 of the distance in which the mountain is covering the turbine. For example, less risky would be, for example, anything. If it starts covering the lower tip, if, for example, no-go area would be if this lower tip height versus 4, and if it is below that, then it starts to be really critical. And the same goes for the other heights.
That's like a safety factor.
Yeah.
Just okay.
For example, our modeling, our in-house modeling today will already trigger any no-go areas in case we have this distance being less than that we expect it to be.